Okay, so thanks. A lot of thanks to the organizers for organizing this workshop, and it's of course a pleasure for me to be back in Cambridge. So I'll be talking about an interesting channel that we came across, and this is joint work with David Lang from IQC and Graham, who's also at University of Colorado. And the good thing about this channel is that it's interesting from the point of view of quantum information transmission, because it exhibits superadditivity of the Coherent information, and I will tell you more what this actually means. But since it has to do with the quantum capacity of quantum channels, I want to first quickly go over the quantum capacity of a quantum channel so that we're all on the same page, and also point out the problems or the parts that we don't understand about the quantum capacity, which then leads to consider a certain class of channels called degradable and antidegradable channels, for which we do know what the quantum capacity is. And then we can use these channels to come up with bounds on the quantum capacity for an arbitrary quantum channel. And I will talk about one of these methods of bounding the quantum capacity in a little bit more detail, and then show how this led us to consider this Dephrasure channel. And then the rest, or the main part of the talk, will actually be to just discuss the properties of this Dephrasure channel. All right, so quantum capacity of a quantum channel, we know that entanglement is a very useful resource in quantum information theory, because it gives way to these things like teleportation, dense coding, entanglement-assisted communication. So one question is, how can we actually generate entanglement? And one way to do this is if two parties, Alice and Bob, are connected by a quantum channel. And the interesting part is if this is a noisy quantum channel, okay? And then the task for the two of them is to use that quantum channel plus local operations on both sides to generate entanglement between them. And one thing that has been shown very early on is that you can give one-way classical communication to those parties for free. So Alice can communicate classically to Bob, and this doesn't change the task. So it doesn't change the capacity quantity. So in a little bit more detail, the way you can think of entanglement generation is that Alice prepares a pure bipartite state in her lab. So the blue color here is Alice, the green color is Bob. And Alice starts by preparing this pure state psi. She holds on to one half of that state, and the other half she sends through n uses of the channel. And we assume an I.I.D structure for the channel, so this is always the same channel here. Then Bob receives the output of those channels. He applies some decoding operation, and then the goal is to bring the total state between Bob's part and Alice's purifying part close to a certain number of E-bits, which means just a maximally entangled state, and we can think of this as just a normal qubit EPR pair, okay? And then if you do this for a finite number of channels, then you will always incur some kind of error, but the goal is that as you increase the block length, this error goes down to 0, and then the quantum capacity of the channel is the largest number of E-bits per use of the channel that you can generate if the error goes to 0 with that protocol, okay? So that's the operational definition of the quantum capacity. And what people then did is they derived the coding theorem for this quantum capacity. So the main achievability part was done in increasing steps of rigor by Lloyd, Shor, and Devitag. And what they showed is that the quantum capacity can be expressed in terms of the coherent information of a channel. So for the channel coherent information, what you do is you take a pure bipartite state, you send one half through the channel, and then you look at the coherent information of the resulting state. Okay, the coherent information is just the negative conditional entropy. So it's the phenomenon entropy of Bob's system minus the total entropy. And then to get the actual quantum capacity, you actually regularize this channel coherent information. So what you do is you evaluate this for more and more number of copies of the channel. You normalize by dividing by n, and then you take the limit n to infinity. And that's what's called a regularization. And that's always a problem, because in general this renders the quantity intractable to compute. Okay? And this is something that quantum information theory is plagued by, classical information theory not so much. For quantum information, there's very simple examples actually of channels for which we know that you kind of have to do this regularization. So the notorious example is the qubit depolarizing channel, which you see here. So this is given in terms of a depolarizing probability p. And with probability 1 minus p, the channel does nothing to the input, but with probability p over 3, it applies one of the 3 Pauli errors to the qubit. Okay? And What's easy to see is that if the probability, the depolarizing probability is 0, then this is just the identity channel. So you have perfect quantum information transmission. Capacity is 1. And if the P is above a certain threshold, which is 1/4 in this parameterization, it actually doesn't have any capacity anymore because of the no cloning theorem. Okay? And now the interesting part is what happens in between those two values of P. Okay? So between 0 and 1/4, we basically don't know yet what's happening. So there's some partial answers. One thing is that if it's an observation that's based on something called approximate degradability, which I will talk about later in a bit more detail. But it's just the idea that if the depolarizing probability is very low, then the channel is kind of almost the identity channel and therefore also almost degradable. And then the superadditivity of the coherent information cannot be too large. Okay, so the coherent information is basically the answer, and what you might be off by is a function that's kind of nice in terms of this small p. Okay, so that was joint work also with Debbie and Graham based on this idea of approximate degradability by David Suter et al. But then if you go to the high noise regime, so if you take the p larger and larger, like towards this point of 1/4, you actually notice that things start to happen which are weird. Okay, so if you take, for example, the p larger than 0.1894, if you evaluate the coherent information for just one copy of the channel, you find it's 0. But then if you actually go to 3 copies of the channel, you find that you get a positive contribution, which tells you that the quantum capacity is also non-zero, okay, strictly positive. And this was done, this is a work by David DiVincenzo et al. Very long time ago in '98. And what they did is they used a very simple repetition code to show this effect, okay? And the 3 here is actually, the 3 is the first n for which this happens. The largest effect is actually for n equal to 5. And then you have more structured codes called concatenated codes, but I'm not going to talk about those. It's just like the gist of it is there are channels and a natural integer, natural number n for which you have the superadditivity effect. Okay, so you have, if you evaluate the channel information for n uses of the channel, you get more than just doing n times, like using a product code on each use of the channel. Okay. And this is what renders the quantum capacity intractable to compute, because you need to, there's no way a priori to control this, okay? There is a way for certain channels. So we can ask now, okay, what channels don't exhibit this? What channels have actually additive channel coherent information? And that leads to the class of degradable and anti-degradable channels. It's just an example, it's not all channels, but those are very well-known classes of channels which do have that. So in quantum information theory, to each channel, you always have a complementary channel that somehow models the leakage of information to the environment. And for a degradable channel, what you now assume is that you have your channel with the sender Alice and the legitimate receiver Bob, and you have the complementary channel to the environment. And you now say a channel is degradable if there is another quantum channel D that allows Bob to degrade the output to Eve's output. Okay, so Bob can somehow model the leakage to the environment. It's an idea that comes from classical information theory in the context of broadcast channels. And David Huck and Shor in 2005 applied this to the quantum picture. And then the nice thing about these channels is that it actually renders the channel coherent information additive. Okay, so superadditivity cannot happen for degradable channels. And then therefore, if you think of the regularized formula for the quantum capacity, since it's additive now, this 1/n just becomes trivial. Well, it goes away, the limit becomes trivial, and the quantum capacity is just equal to the channel coherent information. Okay, so here we know what the quantum capacity is, and you can even compute this efficiently because it makes the coherent information concave in input state, etc. So everything is nice for degradable channels. There's a dual concept called anti-degradable channels, where now instead of degrading the receiver to the environment can degrade to the receiver. So now the environment has a map A, which is not a quantum channel, which allows the environment to recreate every output on Bob's side. And then operationally, you can think of this and then realize that the no cloning argument actually tells you that these channels can't have any capacity. okay, because otherwise it would violate the no-cloning theorem. You can also see it on the entropic level. When you use data processing, you can show that the channel coherent information of antidegradable channels can never be strictly positive, okay? And therefore, if you regularize, you can never get something larger than 0. And the point is, for the depolarizing channel, it is antidegradable for p equal to 1/4 or larger, okay? So that tells us there's no capacity there. And now, we have now these like two nice classes of quantum channels, degradable channels, antidegradable channels, so we might think of using those to upper bound the quantum capacity of an arbitrary channel. So there are now certain methods. This is definitely not a complete list, it's just a list of examples that I know very well. So one thing I mentioned before is now the idea that, okay, a channel might not be degradable, but it might be close to a degradable channel. And then this is something that David Sutter, together with Andreas, Volker Scholz, and Renato Renner did, is to realize that, okay, if the channel is almost degradable in an appropriate sense, then the quantum capacity is almost equal to the channel coherent information, okay? And you have some error terms, but you can somehow control them. And the good part is that this is a function of how close the channel is to being degradable. So that's this approximate degradability notion that works very well when you have something that we called a low noise channel, where you're very close to an identity channel, actually. A second option is that for the task of quantum information transmission, you actually give the sender and the receiver additional power in the form of no signaling or PPT operations, which turn the quantities that you want to work with, turns them into quantities that are easier to handle, okay? So it makes them mathematically more tractable. And those leads to semi-definite programming bounds, where I just highlighted those two papers. So Debbie and Will Matthews did this a while ago, and then Xin Wang and collaborators improved on this. And you get some very nice bounds using this. And the third method that I want to mention and kind of focus on is the idea that you know what happens with channels that are degradable and antidegradable, so you might try to decompose the channel into those parts and then use the properties of these parts. And this was first done by Graham and John Smolin, and they called this additive extensions of a quantum channel. And then Nilanjana, Graham, and I took this idea and generalized it a little bit and strengthened it. And it works as follows. So the main insight here is a result by Michael Wolf and David Perez Garcia, who recognized that even though the quantum capacity is a very weird quantity and not convex in general in the channel, it is convex on channels that have additive channel coherent information. And since degradable channels and antidegradable channels have additive channel coherent information, that invites you to use that principle to try to bound the quantum capacity. And one thing that we realize is that this even holds if the decomposition is into CP maps that are not necessarily trace preserving, okay, which gives you a little bit more power and strengthens the bound. And so this is the content of this paper with Nilanjana and Graham, and actually Dong Yang in parallel had the same idea. So what you do is you have your quantum channel that you want to discuss, and you assume that you have a decomposition into channels that are degradable, those are the EIs, and antidegradable, those are the FIs. And then the upper bound is such that you just need to look at the channel coherent informations of the degradable parts, and then this is the upper bound. The convex sum of this is the upper bound. Okay? And this actually turns out to be very useful. For example, for a depolarizing channel in the high noise regime, this gives you the strongest bound on the quantum capacity that we know now, at least that I'm aware of. Maybe, yeah, I don't know. And this is now actually the starting point for the actual topic of the talk. So when we were working on this bound, another way to look at it is to say that if you have this decomposition into degradable and antidegradable parts, you basically forget about the antidegradable parts, and you only look at the degradable parts where you kind of know what happens, and you take the convex decomposition there. Yeah? And another way of saying this is that we know the channel coherent information of antidegradable channels is always 0. Okay, so you just in principle, you just use the convexity of the quantum capacity, but for the antidegradable parts, you don't get any contribution, right? Because it's 0. And then you might want, and we were thinking, okay, is that actually optimal? Can we somehow improve upon this bound? Because for most states, if you evaluate the channel confirmation for an antigradable channel, most states will actually have a negative Fourier information, okay? And the idea is now, of course, for an upper bound, a negative contribution improves the upper bound, so we kind of want to keep this. So we were wondering, by somehow going to a joint optimization of all the channel confirmations, can we improve that bound? So is that still an upper bound on the quantum capacity, okay? Because we know by convexity of the max function, this will be an improvement over what we do, but it's not clear if it's still an upper bound, obviously, on the quantum capacity. And to analyze this, we can go to an even more restricted and simpler version, which is a flag channel, where you have this convex decomposition into degradable and antidegradable channels, but now you even tell the receiver which one occurred, okay? So there's a flag which allows the receiver to measure which channel did I get, okay? And using the properties of entropy, it's actually really easy to show that the channel confirmation for these flag channels is just this convex combination of the channel confirmations. And this is exactly the conjectured upper bound that we thought might be true. And so if this upper bound was actually true, then this would mean all these flag channels have additive coherent information, right? Because the upper bound is actually the same as the channel confirmation for one copy of the channel, and that's always a lower bound to the quantum capacity. So this whole thing would collapse and just make everything additive. So we were looking at simple examples of these flag channels with a degradable and an antidegradable part, but then we found superadditivity pretty quickly. So upper bound is not true, like the conjecture upper bound, but we don't care about this anymore because we found actually like a nice channel that does that, and this is the Dephrasure channel, which leads me to the main part now. So for the Dephrasure channel, we do exactly that. We take a degradable channel, we take an antidegradable channel, and we mix them together, okay? The simplest non-trivial degradable channel is somehow a dephasing channel, okay? So with a certain probability p, you dephase the input, let's say in the z Pauli direction. With probability 1 minus p, nothing happens. And then you erase the output, okay? That's why we call it, like, that's Graham's creation, so we call it Dephrasure channel because it's dephasing plus erasure. And this part here, this complete erasure is obviously antidegradable, yeah, because the environment gets everything. So it has exactly this form, and what's more is because of this erasure flag that you usually take to be orthogonal to any input state, because you want to be able to tell if there was an erasure, it has this flagged nature as well, okay? So it's exactly of this family that we kind of we're looking at with this conjectured upper bound. From now on, I mean, the probabilities are between 0 and 1, but I will actually restrict to them between 0 and 1/2 because it's kind of symmetric with respect to the 1/2 point. And now the point is that, and the takeaway message, I guess, from the whole talk is that this channel is simple but weird because it kind of checks all the marks on what a quantum channel can do, which is weird and good, okay? So in particular, what we highlight is that it has superadditivity for coherent information already for 2 copies of the channel, okay, which is amazing. Before we talk about the superadditivity, we first want to kind of rule out the regions where we shouldn't look, okay? So we want to ask, is that channel actually antidegradable? Because if it's antidegradable, there's no point in looking for anything because the capacity is 0, okay? So we wanted to check, okay, is there actually a non-trivial region for which this channel is antidegradable? And there is. So we have the channel. You can choose, complementary channels are never unique, but so you can make a choice, and this is a very nice choice. So it has, again, this flagged nature, which is very nice in calculations. Here you have the identity component, which comes from the erasure, and here you have the complementary channel to the dephasing channel, okay? So you have these 2 non-orthogonal states, phi p0 and phi p1. And you just keep the diagonal elements of rho, okay? And we want to find an anti-degrading map that maps the complementary channel to the legitimate channel, okay? And the idea is to use unambiguous state discrimination for this. So what is unambiguous state discrimination? You're given 2 pure states, and you want to distinguish between them, but they're not orthogonal, okay? So you know you can't do that perfectly. And now you can ask, there's certain like different goals that you can have in this discrimination process. And one possible setting is that you say you don't want to make an error. So if you have, if you get outcome 1, you want to be sure it's the state 1. And if you get outcome 2, you want to be sure it's the state 2. Okay, so that amounts to these relations for the P of M elements. But since the states are non-orthogonal, that can't be it. So you need to kind of have like an abort flag where you say, okay, I don't know. Okay, so this is the question mark. And it was shown in a series of papers in the late 80s that the optimal measurement actually has the probability of this abortion of the protocol to be exactly the overlap of the states. Okay. And the idea is now to use that for degrading the complementary channel. Okay, because the idea is that here in this part we can get some information about the input state rho if we can distinguish between the two states phi p0 and phi p1. Okay, so we will do this unambiguous state discrimination with those two states. And the nice thing is that the complementary channel is flagged, so we can kind of measure whether we're in the good identity component, where we have the full input state at our disposal, or whether we have this diagonal information. Okay, so we first measure that flag. If we get outcome 0, where we're handed kind of the full input state, we can do whatever we want with it. And the right thing to do is to erase it with a certain probability. And if we get the outcome 1, then we have basically we have these two states, and then we can try to distinguish them. And we do this unambiguous state discrimination, which will give us an answer, hopefully, but with a certain probability it also tells us nothing, in which case we erase again. Okay? And the cool thing is that if you choose these things in the right way, then this actually antidegrades the map. The only constraint is that here you have to erase with this probability, and this needs to be positive for it to be a CP map. Okay, so that's the constraint that you have. So this is this constraint here. And if you plot this in the PQ plane, it turns out that the channel is antidegradable in this region here, which for us is now to say, okay, we don't look for anything over there because we know the capacity is 0. Okay, so whatever happens will happen in here. Yeah. Okay. To talk about superadditivity, you need to know the optimal single letter coherent information because that's kind of your benchmark. So it would be nice to have a formula for this. Okay. And here, this flagged nature of the channel helps you a lot in calculations. So one thing you can do is you can rewrite the coherent information in this form, where it's basically given by the coherent information of the dephasing channel plus the input entropy of the state that you put in. Okay. And since the dephasing channel is appearing here, this suggests that the optimal state will actually be diagonal in the dephasing basis because those get through the dephasing channel, right? And it turns out that this is true. This is actually, if you write it down in the right way, this is just simple calculus. And we get this almost closed formula for the single letter coherent information, where you just now optimize over a single real parameter, and then that lets you find the optimal single letter coherent information. And if you do that in the PQ plane, you notice a couple of things happening. So we know from before we have this antidegradability region here. If we're in a low noise regime, then this optimization will always yield the completely mixed state as the optimal input state. So the Z would be 0 in the block representation. But then as and this is true until a certain curve for which we have an analytical expression. And then as you go towards the region of 0 capacity, you notice that the optimal input states begin to be biased. And then they become 0 here at a certain point. And you don't really see that very well here, but the region between red and green is supposed to be blue. And within this region, we actually find the superadditivity. Okay. So one thing when you think about superadditivity of coherent information, the go-to thing is the repetition code, because we know from the depolarizing channel that works well, and it's a good first thing to try. So, but we actually do a little bit more. We take a weighted repetition code. So we have some bias between the logical 0 and logical 1. Okay, this is this lambda here. And we also know from our analysis before that for n equal to 1, this is actually the optimal single letter code as well. Yeah? Because a code that's diagonal in the Z base is nothing else than a one-letter repetition code in a way. Yeah? So, so we now want to evaluate the Coherent information for these repetition codes. And if you look at the tensor channel, if you take n copies of the Dephrasure channel, you will, if you expand this tensor product, you get channels of the form. You have a certain number of dephasing channels and a certain number of erasures. And because of the fact that the erasure flag is always orthogonal to any input state, you have these partial erasures, and they're all orthogonal to each other if there's a different erasure pattern. And because of this direct sum property of the phenomenon entropy, the Coherent information just splits up into these different erasure patterns. Okay? And the nice thing about the repetition code is that all the partial erasures actually cancel because they have the same effect on the Coherent information for the channel and for the complementary channel. Yeah? So all you're left to do is to evaluate the action of having dephasing in every slot, in every tensor factor on the repetition code, and that's pretty straightforward to do. Okay? And this leads again to a formula which is not completely closed, but it's we reduce it from a pretty difficult optimization problem to an optimization problem over one real parameter, which is this lambda, the bias in the repetition code. And it's given by this formula. Sorry. So this U quantity here is again is a function of the lambda, the P, and the N. But once you fix P and Q for the channel and N for kind of the block length you're looking at, the only free parameter is a lambda. And then you optimize over that and you get a value for the repetition code Coherent information. Okay? And even though you know this is not going to be optimal, it's a lower bound to the quantum capacity. So if this is either non-zero or more than the single letter Coherent information, you know there's superadditivity. Okay? And it works out. So what I plot here is the magnitude of the superadditivity. So this is the single letter value, and this is the normalized Coherent information that you get from a weighted repetition code. And I plotted here for n equal to 2 and n equal to 3. And you see that in this fish-shaped region here, you have this kind of island of superadditivity, where purple is large and blue is low. And you see that as you increase the block length of the repetition code, the rate goes down, which is, it always happens for repetition codes, right? So if you do this for 4 and 5, you notice that this is now 10 to the minus 4 instead of 10 to the minus 3. But you still have the effect. And you see that especially in this region here that is crossed by the Q equal to 3p diagonal, you have like the kind of maximal effect of superadditivity. And it also holds in the extreme form where the single letter Coherent information is already 0, but the repetition code still gives you a positive rate. So you know there's still quantum capacity even though the single letter quantity is 0. Okay? So that's, you say that the threshold is increased because you push the threshold of positive quantum capacity outwards. Okay? We also have some more elaborate codes that are not repetition codes. One example is here, this code on 3 input qubits. So the 3 rightmost qubits are sent into the channel, and the psi 1 and psi 2 are just arbitrary pure states that you optimize over. And actually, in concurrent work with Johannes Bausch, who is here, I don't know if he's here, but he's at Cambridge, we used a neural network state ansatz to optimize the Coherent information, and that gives us even, in certain cases, even better Coherent information. So I'm happy to talk about this offline if you're interested. Yeah, one thing that we at some point thought to be true is that what we know in a single letter case that diagonal codes are always optimal. We thought that would also be true for any end, but that we found these non-diagonal codes, so we're actually not sure anymore. So that's kind of one of the open questions. Here's another plot where you see very nicely this increased threshold. So this is now along the P3P diagonal, for which we saw like the largest effect of superadditivity. And the black line is the single letter Coherent information, which becomes 0 over here, and then you still get positive Coherent information from repetition codes. Okay? And since these results are all very numerical, I quickly wanted to say a little bit about the kind of methods we used for the numerical optimization. So one thing is when you try to optimize the query information, the query information is always 0 if you put in a product state. Okay, so you can never generate entanglement between two parties if you put in a state that's product between the reference and what goes into the channel. Okay, that's pretty clear. And so now if you're in the high noise regime where kind of most states have negative query information, then all these product states will be local maxima. Yeah, so if you use something gradient based, then you're very likely to just get stuck in one of these local maxima, but that's not what you want, right? Because it's pretty easy to just write down a pure state, product state that gives you 0 query information, okay? So the idea is now to switch from gradient-based methods to something that's somehow global and gradient-free, okay? And the nice thing, there's actually a lot of biology-inspired numerical optimization methods. So some very well-known examples are genetic algorithms, there's artificial bee colonization, there's ant colonization. They all take some biological idea and work that into the math. And one thing that I want to highlight and that we use for this work is particle swarm optimization, which is a very simple thing. So the idea is that you probe the landscape that you want to optimize over with agents or particles. And the idea is now that each particle records the function values as it wanders around, and it records the best personal, and everybody knows about the best global position. This is like a very primitive form of swarm intelligence, where everybody knows where's the best one that I had and where's the best one that anyone has seen. Okay, and then you give the particles velocities, and you update the velocity with 3 parameters. One is it kind of gravitates back to the personal best. One thing, it gravitates towards the global best, and one thing is it just keeps moving. Okay, so there's a certain inertia for every particle, and it's best seen in a picture. So there's like a test function you always use for global optimization, which is called the Ackley function. It's a nasty thing, but the cool thing is that it has a lot of local minima, and it has one global minimum at 0, 0. Okay, so it's kind of a challenge for optimization techniques because gradient-based methods will most likely get stuck in one of these local minima. Okay, and so now if you do the particle swarm optimization, so remember the global minimum is at 0, 0, this red dot. And let's let the particle swarm start in one of the corners. I mean, ideally you would try to cover the landscape uniformly, of course. But here you kind of see quite nicely that if you now do this, the swarm starts moving somehow. And then pretty quickly it kind of finds the global minimum, and then it doesn't get away from there. And then it kind of converges to the global minimum, okay? But it kind of avoided all these little local minima there using this idea of swarm intelligence. But it's actually very, we found it to be very powerful, and I think more people should use this for quantum information problems because it seems to be quite nice actually. All right, enough for the numerical methods. One more thing I want to touch is private capacity of a quantum channel. So the private capacity of a quantum channel is the highest rate at which you can transmit classical information privately, so private against the eavesdropper. And we also know a coding theorem for the private capacity. It's again a regularized theorem, so there's problems. This time, instead of the channel query information, we use the private information, which is you take a quantum state ensemble with mixed states, and then you look at the difference of the whole label quantities with respect to the receiver and with respect to the eavesdropper. And then to get the actual capacity, you regularize this private information, and then you, again, there's channels for which this is strictly superadditive, which tells you it's hard to compute this. Okay, so this was one of the first results for here was the BB84 channel for which Joe with Graham and John showed the superadditivity. So this again tells us, okay, there's a problem here, and it's interesting to look at this, whether you can have superadditivity. And another thing is that it's also interesting to look at the relation between private capacity and quantum capacity. So one thing operationally is that quantum information transmission is always necessarily private. So the private capacity is always at least as big as the quantum capacity. And this also holds on the entropic level for the information quantities. But the question is now whether you can have separations here. Yeah, so we know of examples where we have a separation. Okay, we know where there cannot be any separation. So for degradable channels, Graham showed that all these capacities and information quantities are actually equal. So for a degradable channel, private classical information transmission is somehow the same as quantum information transmission from this point of view. And it also turns out that anti-degradability is not just a zero constraint for quantum information transmission, it's also a zero constraint for private information transmission. Okay, so anti-degradable channels have also zero private capacity. And there are weird channels for which the quantum capacity is zero, but the private capacity is non-zero. So those are, for example, some entanglement binding channels. And that gives way to the effect of superactivation of quantum capacity, where you take two channels that by themselves have zero quantum capacity, but suddenly if you use them together, they have positive capacity. Okay? This was the famous result by Graham and John Yard. And so what we are now interested in is kind of try to show a separation between at least the channel coherent information and the private information, okay? Because that's kind of the first step in showing these separations. And we did a lot of numerics. This is much more complicated to do numerics with than just coherent information. But what the numerics kind of showed or yielded was that ensembles of this form should be optimal for the private information. So all you do is you take plus and minus states, so equal superpositions of 0 and 1. You give them a bias, so you kind of mix them together, but you actually have equal probabilities of which ensemble you use. And then if you optimize over the lambda parameter, then you see that this is again along this P3P diagonal. The blue line is the optimal channel coherent information, and the red line is the prime information you get from this ensemble. And you see like a very nice and clear separation here. And we think that this is actually the optimal value, but that's one thing that we couldn't prove, and this is one of the open questions. And that's unfortunate, because when you want to talk about superadditivity, as I said before, you need to know the optimal value for the single letter quantity, right? Because otherwise you can't compare it. So the question is now, do we have superadditivity of prime information, as we did for coherent information? And then going forward from that, do we also have a separation of capacities? But that's, of course, much harder to show, because you need to, for this separation, you basically need to show, you need to know the quantum capacity, and that's hard. Okay, so these are kind of the open questions surrounding the private capacity. Okay, so to sum up, we had these, the quantum capacity is a very problematic quantity, but we have ways to upper bound it. One way is this decomposition into degradable and anti-degradable channels, and this method led us to think about certain channels that have this form. And the Dephrasure channel kind of popped out as a very simple example that checks all the marks on the weirdness chart. So we have superadditivity of coherent information, we have the separation between private and coherent information. We possibly have superadditivity of prime information. I think this is true, but we can't show that yet. So that's one of the open questions. Another open question would be to get tighter bounds on the quantum capacity, of course. I mean, that's for every channel, that's a goal. Also, there is a quite large gap between this increased threshold we get from repetition codes and this region of anti-degradability, so it would be nice to somehow close the gap or show that the zero quantum capacity region is actually much larger. And we can also try to use this channel for different contexts. So for example, there was a recent work by Elton and Juntao at MIT together with Peter Shore, where they looked at classical information transmission where you have entanglement assistance, but it's limited. Because if it's not limited, we know from the famous result that everything is additive and nice. But if you limit the entanglement assistance for the sender and the receiver, you can actually show that this is super additive. But the channel they used was a bit complicated. So the hope would be that the Dephrasure channel, since it's very simple, like you can calculate with it, the hope would be that this would somehow give a nicer example of superadditivity in this context. We don't know yet, so that's ongoing work. And another thing that I'm kind of curious about is there was this recent work on these alpha bit capacities by Patrick Hayden and his student Jeff. And they had a way of kind of explaining superadditivity of coherent information through these alpha bit capacities, and since the Dephrasure channel is a very easy channel for which we see these effects, it might be nice to try to nail this connection down a little bit more and kind of try to investigate this a little more. Yeah, but that's all I got. Thanks for your attention. Thanks.
This decomposition of channels into like degradable and degradable, do you know how general it is? Like, for which channels can you do this? Or
you can do it for every channel. So the Krauss decomposition is one feasible point, but everything is degradable there. So this is kind of, you want to do better than that, but you can always do that. Yeah.
I have a question. Since you like playing around with this, have you considered epsilon anti-degradable, kind of, nearly anti-degradable channels as well?
To do what? To get upper bounds?
Yes.
So that is in the same paper. I mean, they looked at this. The thing is, for the depolarizing channel, that actually doesn't give you anything.
Yeah, but there are
there's other channels, of course. Yeah, I mean, depolarizing channel is kind of the go-to channel. Kind of part of our work is maybe this should be the go-to channel. But yeah, definitely. I mean, you can think about that. That's a well-defined thing. And for these epsilon antigradable channels, the capacity is small. Like,
yeah, but your bounds are better.
in the high noise regime, there.
In the end, this fineness inequality just forms everything. So.
Yeah. So for the high noise regime, it doesn't seem to be optimal, or the best method. But it's definitely a possibility. Yeah.
Show this nice fish diagram and show the regions of superadditivity.
Yeah, so I have to go through the
Okay.
particles one.
No, don't worry, don't.
No, it's there. It's there.
Yeah.
Yeah, this one.
Do you have any intuition why?
Why it's there?
Yeah.
Not really. I mean, it's kind of. I guess there is an intuition of why it should occur for lower values of the dephasing probability somehow, because the states get through almost unchanged, but then it's the erasure so the erasure needs to be high. But yeah, no, unfortunately we were still thinking of how to make sense of where these regions are and why, yeah. And this is also just repetition code, so this is, this is definitely not the optimal values for the channel information. Yeah.
Questions? So do you have any chance, for instance, to find these kinds of examples where Q2 is 0 but Q3 is not? I mean, if you try that. I mean, come on, I mean, everything.
I mean, kind of, you do see it here. With repetition codes, but you like there's no channel for which you know the optimal input state for 2 copies.
Okay.
And you need to know that because you can never talk about superadditivity then, right?
But there are these examples of
yeah, they exist.
Elkus et al. No?
Yeah, they do exist. They're very flexible.
Oh, okay. Yeah, that's true. So where you have this one, you know where the point is where it suddenly jumps, right?
Yeah, you more or less can predict it.
Or you can tune the parameters so that it's wherever you want it to be. Yeah, I mean, okay, those channels you have. Okay, that's true. Yeah. But, yeah, for here, I mean, for this one, we don't know.
Right, so if there are no questions, let's thank all the speakers.